I know, as I'm saying.
All right, good morning, everyone. So just a reminder, at the end of class today, just drop off your homework at the front before you head out. Our last homework for the course is Chapter 30, which we started in lab this week, or you will start in lab this week, if you have lab later this afternoon. Electromagnetic induction is what we'll spend the last 2 lectures fleshing out. We're going to talk about magnetic flux, Lenz's law, and Faraday's law. All right, so the purpose of today's class is to get a little bit more familiar with electromagnetic induction. Electromagnetic induction is very important because it's responsible for much of power generation. And we'll talk about a little bit more about why this is true. So, just kind of connecting to what we've done before, we already know, or we've learned, that a current produces a magnetic field. Right? And this was originally discovered by accident 200 years ago. Ørsted in 1820 discovered, a current. There was a compass needle by a current, and it caused the compass needle to deflect. Right? So current produces a magnetic field. About 10, 11 years later, Faraday and Henry started to think about, well, if a current produces a magnetic field, is it possible for a magnetic field to also produce a current? And that is now called Faraday's law, so in fact that is true. So let's talk a little bit about why that's true and just actually look at the experiment, or a version of the experiment itself. So here I have a series of coils, and these coils, it's very similar to what you will, or what you have built in lab this week. Basically a solenoid connected to a current meter. And different solenoids just have different numbers of loops. So let's test out Faraday's and Henry's prediction. If I bring a magnet towards a loop, does a magnet produce a current? Well, the needle isn't really measuring any current. Okay, but something interesting happens when the magnet is moved. The needle deflects. And notice that the needle deflects in opposite directions depending on whether I move the magnet in or out. It depends on the orientation of the magnet. If I turn the magnet like this, for example, I get a very minimal change in the needle. If I do it rather slow, it doesn't move too quickly. If I do it really rapidly, it changes a little bit more. Now, what about if I move down to the bottom solenoid here? There's just much more loops of wire. Well, roughly with the same speed, the needle deflects much more. But still, if I turn it by 90 degrees, I'm not getting much of a reading here. So, as Faraday was looking at the experiment, looking to see whether current was measured, you notice something interesting. It's only when there's something changing with the magnet. Something is actually changing here. So we'll quantify that a little bit more. But in particular, what Faraday looked at was basically, he found something very interesting happens is when you turn a circuit on or off. So here I have another solenoid. And this solenoid is not powered, it's just connected to a big galvanometer. And a galvanometer is just a very sensitive, we can think of it just as a very sensitive current meter. So this is not reading any current. Let me come around to the front here so I can see this a little bit better. Right in the center here. Now, here's another solenoid. And this solenoid I'm going to connect to a battery, so there's actually current running around like this. So this solenoid will produce a magnetic field, right? That magnetic field inside the solenoid is mostly axial to the solenoid. So if I put this inside here, still nothing happens. Now let me turn it on. So notice that needle jumps as soon as I connect it. As soon as I disconnect it, there's a large current that spikes in the other direction. So nothing's happening. I send current through the solenoid, and this solenoid is just nested on the inside. They're not electrically connected. Something only happens when I turn it on, and it's on now. But when it's running, nothing happens. But when I turn it off, there's a large current that is produced, but the needle deflects in the opposite direction. So this was kind of, in a sense, discovered by accident. And something very interesting is happening when the circuit is turned on or off. So what are the differences between these two cases and what are the similarities? Well, in this case I have a permanent magnet producing a magnetic field, which is going through these loops, which is changing as I move the magnet. In this case, I have an electromagnet still producing a magnetic field, which is changing. The magnetic field is only changing, though, when I turn it on or off. The field goes from 0 to some number, right, when I turn it on or off, but when it's running constantly, it doesn't change. So let's see if I can see a similar effect if I just keep this running. And okay, there's no current, but if I pull it out, I'm changing the field just by moving it, and then I put it back in, and I get a induced current again. All right, so these observations can be put together in terms of what is called Faraday's law. And Faraday's law says, as we've seen in the lab, but EMF is induced depending on a changing magnetic flux. So this is Faraday's law. Now, let's just talk about each of these terms. So notice the EMF that's induced depends on the flux that is changing. So EMF, this is electromotive force. Electromotive force can either come from a battery, which separates charges, produces an electric field, causes charge to move. That's how you have current. But this electromotive force is an electric field. Its underlying source is an electric field, but this electric field is an induced field due to a changing flux. So its source is not charged. All right, so I'm going to write this is the electromotive force. And it has a very special property. You'll remember that normally, if I do the line integral around a closed loop for my electromotive force, or if I do that for the voltage, what I get is 0. That's the loop rule. Right? But for induced electric fields, if I take a closed integral around a loop, I get something non-zero. So it's still producing an electric field. This is the induced electric field. All right, now, what about this term right here, phi sub b? So we've talked a lot about phi sub e, electric flux. Phi sub b is very similar to electric flux, instead it's not really measuring a flow rate of electric field lines, it's measuring the degree to which magnetic field lines penetrate through a closed area. So we define magnetic flux phi sub b to be the integral. This is a surface integral of b dot dA. The units are called the Weber. 1 Weber is 1 Tesla meter squared. Units for magnetic flux. So, yes?
Should that be a double integral or just a...
Yeah, so we could write this as a double integral because you're integrating over, if you're in Cartesian coordinates, you have a dx dy. Right? Just a flat surface. So imagine dipping a hoop into a stream, right? What is, if we're really measuring how much these field lines penetrate through the surface, it's really going to depend on, the flux really depends on 3 factors, right? The flux depends on the field strength, right? If the field strength has twice the strength, then you have twice the flux. It depends on the area. The area is twice as large. You're capturing twice as many of those field lines. So area of loop. And finally, the orientation. The orientation between the area and the loop. Because it really matters how that loop is inserted into the field, because if it's parallel to the field, nothing goes through the loop. It's a measure of the amount that those field lines penetrate through the loop. So those are the different ways flux can change. Now, we're going to, so these 2 quantities down here, well, so basically whenever the flux changes, and how do we change the flux? Well, we change it by changing one of these 3 quantities. Whenever it changes, you produce an EMF. What does an EMF do? When there's a conductor, it causes charge to move, gives you a current. Okay? So EMF, I can write as I times R. This is when you have a conductor. When you have a conductor with a certain resistance R, you get a current, which is induced. So this current right here is induced because of the electric field. One more thing I want to mention about this law, and then we'll look at some applications, is this negative sign here. What is this negative sign telling us? Well, I'm going to refer to this negative sign as Lenz's law. And Lenz's law basically tells us the direction of the EMF. And you might ask, well, how does EMF have a direction? Right, well, EMF, what do we mean by EMF, electromotive force? We really mean electric potential difference. Right, so we're really talking about a change in electric potential. And we're saying it's non-zero around the loop. So would you agree that if I have a simple circuit with, let's say, 1 resistor, what direction is the current going to flow in that circuit? Clockwise or counterclockwise? Clockwise. Now, if I take the battery and I flip it, what direction does the current flow now? Counterclockwise, right? So the current depends on the orientation of the battery. So Lenz's law tells us the orientation of the EMF, in essence. And what the negative sign says is the EMF always opposes the change in flux. So to put it another way, when I have a conductor, I get an induced current, and that induced current produces an induced field, induced magnetic field, and that induced field will oppose the change in flux. So I'll write it this way: B induced from I induced give, this opposes change in magnetic flux. So the key word here is opposes, meaning opposite, and the change. It doesn't oppose the flux, it opposes the change in flux. It doesn't matter whether the flux is, there's a net flow right or left, it just matters what direction the flux is changing. So whenever you're changing, you're looking at a difference between one and the other. Yes?
So the EMF is going to give you a voltage in the direction that the current would flow if it was in a circuit. So which way is positive in a circuit?
Well, either which way is positive in a circuit? Well, that's a great question. It's kind of, if I have a loop of wire, right? We talked about how, you know, this is just a loop of wire right now. This loop, if it's flat, the surface between it, let's just say it's a tight rubber membrane, it has a certain area vector that's perpendicular to the surface. Okay, area vector. Now, there's nothing moving. There's no preferred way to orientate that area vector. We could point it to the right, like I've sketched it here. I could sketch it to the left. Okay. So similarly with flux, so when I calculate my flux, depending on which way I'm thinking of my area vector, I could get a positive or negative number. It doesn't really matter. What matters is the change, whether it's increasing or decreasing. If the flux, let's say the flux is positive, because my field is also flowing through the loop in this direction, so I have a positive flux, and that flux is decreasing, the current will flow through the loop in such a way as to rebuild or to restore that field. The induced field wants to add to the field that is weakening.
Right. You use right-hand rule to figure out the direction of the current based off of the direction the field should be going to counteract the change in flux, right?
Exactly. Yes, exactly. So your induced field produced by the induced current follows the right-hand rule, where your thumb is the current on your right hand and your fingers curl in the direction of the field. Excellent. All right, so let's try, take out your voting cards. Let's just try an example of this now. And all right, so I have a loop of wire, and I have a current, a long straight current next to that loop of wire, and that current is being pulled away from that loop of wire. So as the wire is moving down, what direction is the induced current in that loop? Clockwise, counterclockwise, or no currents. I want you to think quietly for about this, and then we'll take our individual votes. Okay, so let's, does anyone need more time here? Give you a few more moments to prepare your vote. Okay, and get ready to prepare your vote. So 3, 2, 1. All right, let's take a moment. Convince your neighbor of the direction of the induced current in the loop. All right, in a moment, we'll get ready to prepare your vote again, see if anyone's changed their mind. All right, let's take a vote here. See if we've arrived at a consensus. 3, 2, 1. Right. So A's and B's are most popular, clockwise or counterclockwise. Still a bit of a disagreement. We haven't really arrived at a consensus here. So someone who has A, for example, let's start out with that one. Can you offer an explanation as to why you picked that? Yes.
So if you consider the rod when it's not moving, the square has a high flux through it going into the board. And then as it's moved away, that flux decreases. And so the square wants to fight that decrease. And so it adds a magnetic field in the same direction going through the square. And that means that the current goes this way, clockwise.
Okay, excellent. So the field through the loop is into the screen, is what you're saying.
Yeah.
And as the wire is moved down, this field strength through the loop is decreasing, so the flux is decreasing.
Yeah.
So the induced current tries to rebuild or restore the field which is getting weaker by adding a field into the board. The only way you can add a field into the board through the loop is by, in the loop, having a current that goes around this direction to get a field into the board on the inside. All right, yeah, so A is correct, clockwise. Here. Questions? Clarify this one. We'll try a couple other examples here. Yes, Ben.
Why do we need the negative sign in the equation if we just use the right-hand way to figure out the direction?
So in practice, we won't really need the negative sign. When you practically solve a problem, you won't need to make the negative sign. Now, strictly mathematically speaking, you need the negative sign for the reasons of this area vector which I was speaking of here. Let's say you knew nothing, you had no physics, you weren't thinking about the physics at all, and you were just taking it to be a mathematical equation. Once you had mathematically calculated the flux, right, this would just spit out for you what the answer is. But it's the negative sign, it's built into the equation by really this Lenz's law. All right. Any other questions here? Let's try another. Actually, on a second here. I'm going to try one on the. Let's try one on the board here. So. Let's go back to the solenoid example that we were looking at. Well, I had some solenoids up here on the front counter. Now, so let's say I take an iron core, and I take that iron core and I wrap it with some wire. Right, and as it's sketched so far, there's not any current in this circuit. And I'm going to add a switch here as well. But if I add a battery, so I'll add 2 batteries in series. As soon as I close the switch, I'm going to have current. Correct? It's going to be current. Now, we've talked a lot about solenoids so far and the magnetic field that they produce. And solenoids are very useful when you want an electric signal to trigger some kind of mechanical motion. So let's say I have another nearby circuit. Let's say I have another solenoid. It's not connected to this solenoid, but it's just another solenoid over here. And the wire is coiled tightly around the solenoid. And this circuit just has a current meter on it, as such. So here's the question is, let's say the switch is closed. Now, close the switch. Immediately after, the switch is closed, which direction, if any, does the current flow through the ammeter? All right, I'll give you 3 options here, because there's only really 3 options for the direction of the current through the ammeter. It could be left, could be right, or it could be 0. Will, do you have a question?
Yeah, which side's the positive end of the battery?
Oh, the longer end. Yeah, so longer. That's 2 batteries in series, plus minus, plus minus. Okay, so yes.
Is that assuming the circuit with the ammeter still has the battery in it?
No, this circuit has no battery in it. Just it has a current meter, such as the battery's only in this circuit. Okay. So I close the switch. Immediately after the switch is closed, what direction through the ammeter does the current flow? So I want you to quietly, individually think about this. No discussion at this point. Think about these principles, and then we're going to take a vote here in a moment. Yeah,
This
cool
is
question.
depicted as if there's just 2 circuits kind of sitting next to
They're parallel to each other, but they're not wired
each
together.
other. Right, they're just like in the same.
They're electrically isolated.
Okay.
Yeah, Ben?
By right, you mean like right up, from right to left?
Yeah, from what direction
Pointing, like,
does it
around.
flow through I? Does it flow to the right? Does it flow to the left? Or is there not any current through A? So let's take a vote here. And final moment here to prepare your vote. So do you think it's A, B, or C? Some people are still thinking about this here. A little bit of disagreement. Okay, take a moment. I want you to explain to your neighbor the direction of the current, if any, through A, the ammeter.
like grandmother
All right, let's discuss. We'll take a vote here. It's going to be. Have any? So prepare your vote. And 3, 2, 1. All right, we have about 70% saying B, which is correct. It goes to the right through the ammeter. So let's just discuss why that is. So as soon as I close the switch, I have a current in the circuit that goes like this. Okay? Now as the current comes up and around the loops like this, that means I have a magnetic field inside the loop or inside the solenoid, which points leftward, and it's a uniform field inside the solenoid. There are some edge effects at the corner where it starts to either converge or diverge the field, but it's a leftward field because the switch is closed. Now, some of those field lines, if I extend it out, they actually produce flux through these set of coils over here. And that flux is in this direction. Right? So I have a rapidly increasing magnetic field in this direction. Lenz's law says, while this region of space doesn't like a rapidly increasing magnetic field, it tries to oppose it, tries to bring it back to zero. The way to do that is by producing an induced field to oppose. So this B increases rapidly. When you close the switch, it suddenly bursts on to the left. This one doesn't like it. It tries to bring it back to zero. So it wants to induce a field B induced opposes the B that's increasing rapidly to the left. Right, tries to bring it back to zero to make the net field zero. So when I add B induced plus the B that's rapidly increased, it tries to bring it back down. And the only way to get a rightward field would be if the current goes this way around the loops, so that the field points to the right. That would give you a current to the right through the ammeter. So we have right here. Yes, Carson?
When you say wants to, I understand that's kind of a personification of the region of space.
Yes.
Like what does that actually mean? Like why is it?
Excellent question. So, and hold that question for just a moment because I'm going to address that in just a moment here. Because there's something new happening, which is there's some new physics in this law, this Faraday's law. Something new and unexpected is happening here. All right. So, is everyone comfortable though with the direction? Okay. So just to follow this up though, what about long after switch is closed? And think about this quietly. So long after switch closed. Give you a moment to pick your answer, left, right, or zero. Let's take a vote here. 3, 2, 1. Yeah, you're correct. It is zero because nothing's changing. No current. There's only current when the magnetic flux is changing. There's no flux changing, so there's no current. Now, by the way, how much flux would we say is actually going through these loops? Well, if you were actually to calculate the flux, you'd have to find the flux through one loop and then multiply by the number of loops. So let's say that there's n loops here. The total flux through this set of coils magnetic flux total would be n times the magnetic flux through 1, because you have n different coils. So that's one way, if you really want a larger current, that's why you use a solenoid, you just create a lot of different loops. You can change your voltage. And by the way, that's how transformers work. You can get larger voltages or smaller voltages just by varying the number of loops. Step up or step down your voltage. Question?
So it's just, how come it isn't dependent, like how come the flux of the last loop wouldn't be any less than the flux of
That's where the geometry is going to, it's going to depend on the geometry really, how long the solenoid is, how strong this field is, how much current is being drawn because of this chemical EMF, this battery right here. So yeah, it's true that the details of it, this loop could have less flux than this one if the field is really spreading as dramatically as I pictured it here. Yeah, that's where but that's where it would get analytic. Here we're just, that's a great question though, yeah, to actually do the calculation. All right, so, and then just finally, what would happen immediately after you open switch? I want you to think about this immediately, quietly, immediately after opening switch. Take a vote here. 3, 2, 1. Okay, correct, it's left. And the argument would be very similar, except everything is just reversed. Now the B field doesn't rapidly increase, it rapidly decreases. And this coil doesn't like the rapidly decreasing field, so it tries to rebuild or restore. Instead of canceling it, it tries to rebuild the field that was there. So it goes to the left. Okay, so this is Faraday's law. This is Lenz's law. Now, let me get back to Carson's question here about why does that second solenoid not really like the fact that the field is changing over here. All right, and to answer this, really have to point out that there's some new physics that's taking place here, because this law says something pretty powerful. And what it says is area, if you change the area or the orientation, this is really geometry. These two factors are really geometric, or having to do with, I might call motional. They're motional factors depending on loops that are growing or shrinking or rotating. And we could kind of, from what we already know about electric and magnetic forces, we could already kind of deduce that there's some kind of induced current. But this last factor right here, this B field changing, this is really where the new physics is. Just changing the B field alone induces an EMF. And that EMF, by the way, is induced via, which means regardless of whether or not there's a conductor there. All right, so why is that? So imagine I take a conductor, and I take that conductor and I start to move it. Through a magnetic field. So I'm going to take a region of uniform magnetic field. This is a region of uniform magnetic field B into the board. And I'm going to take a conducting rod and put it inside this region of uniform magnetic field. And I'm going to move it to the right with speed v. So this is that's just a conductor. All right, and we know conductors are a sea of electrons which can move more easily. Let me say that this conductor has a certain length, I'll call L. So what's going to happen as that conductor moves to the right? Are electrons, which direction, if any, are electrons going to be pushed? Well, let's just take a vote here. I guess up, down. Let's just say up, down, or none. Up, down, none. Discuss with your neighbor. We'll take a vote here. Field is empty. Yeah. Yeah, we'll do that first. Okay. All right, so this is the right-hand rule, which we've learned about already. Now, so which, let's just vote here, see we're all on the same page, up, down, or none? Okay, I'm seeing down. Down is correct. Yeah, the electrons experience a magnetic force, and they start to pile up at the bottom. Right, if you don't want to think about electrons, you can just think about positive charges that are moving. Because if I have positive charges which are moving to the right, and I have a magnetic field which is into the board, I have a force on positive charges which are up. So for every positive charge that is sitting here, it experiences a magnetic force which is up. Right? If I move a positive charge up, I leave basically a negative behind. Right? So what's happening as you move this conductor through the magnetic field is you're separating charges. Now that separation of charge can't happen forever because as you pile more and more charges up top here, now there's also an electric force on every additional charge that wants to move, which pushes it down. It's the electric force. Eventually, those two forces balance each other out and charge doesn't move anymore. But you've built up a bunch of positive charge up here, a bunch of negative charge up here. And this we call motional EMF. Right, there is, between the two ends of the rod, there is a delta V, which is our EMF, between the two ends of the rod, just because of the fact that the rod is moving. So the top of the rod has a high V, the bottom of the rod has a low V, just from the fact that it's moving to the right. So we can use some simple, physics when we talk about equilibrium. This conductor reaches very quickly electrostatic equilibrium. And in electrostatic equilibrium, we would draw a free body diagram for that point charge in the middle, and the forces would have to balance. So we would just say that the magnetic force has to equal the electric force, which pushes it down. The magnetic force is just equal to QVB. The electric force is just equal to QE, whatever the electric field is. So we get VB equals E. We see there's a relationship between E and V just due to the fact that the conductor is moving. So in a sense, we could talk about an electric field being induced just by the fact that I have a magnetic field, which is somehow changing because there's something changing here because the conductor is moving. All right, now, what about the potential difference between the two ends of the conductor, delta V? Well, delta V is, if I imagine the top and the bottom to be like plates of a capacitor, I could approximate, this is sort of approximately the delta V, which is the EMF, is just going to be equal to E times the length of the rod if the electric field is constant. Let's say it's kind of a thicker rod, right? So the field, it's kind of like a capacitor field in between. So what I get is basically VLB is this is the induced EMF. Which we're really calling, it's induced by the fact that there's motion. So it's the motional EMF. It's induced by the motion of the conductor in the field. So in this case, the EMF is there's not a chemical source of the EMF, there's a motional source of the EMF. Yes?
Are these vector quantities or scalar quantities?
So, which quantity?
V, E, and V.
In the equation, I've written them as scalars because in the picture I already accounted for their vector nature, pointing up and down. And here I'm just balancing forces. So when I balance forces in the vertical direction, I just write the magnitudes. Yeah, so forces are vectors, but here I'm just writing the magnitudes, balancing them out. And then V, of course, is always, electromotive force is always a scalar quantity. All right, so let's just test this out. So let's say I have a square conductor, and moving through a uniform magnetic field. Which of the figures, A, B, C, or D, shows the correct distribution of charge? Give you a moment to think about this one here. And get ready to prepare your vote. Count of 3, 2, 1. Purple, yes, V. Because V crossed into B outwards gives me a force on the positive charge, which is to the right. There. So I get a separation of charge here, which is horizontal. I get a motional EMF that is horizontal just because I've changed the direction or the orientation of the fields here. Okay, so this, now, okay, you might say, all right, well, I have an EMF that's induced, but how does this connect to Faraday's law? Because so far nothing really happens here. But I'm going to take this same system right here, and I'm going to add a conducting rail. And then we'll make the connection to flux. So let's say I'll draw this in red. I'm just going to add another conductor to the system. And this conductor is just a rail. I'll make it thick, so it's just a conducting rail. Okay, what direction would the current flow in that loop as the rod rolls to the right? Clockwise or counterclockwise? Counterclockwise, right? Because that circuit is like, well, it really looks like you have a battery like this, right? Plus end, negative end, so the current is going to flow around in the counterclockwise direction. It's really like a circuit now that you have. Okay, so we can say that the EMF equals IR. Let's say the resistance the wire has some resistance. So conducting rail has resistance. Has resistance R. So EMF equals IR equals VLB. So we have an induced current which equals VLB over R. Flowing counterclockwise. Okay, now you might think, well, is this free energy? Right, conductor is just rolling along in a magnetic field. I got a current, I put a resistor in that conducting rail, and now I can run a light bulb, and it doesn't cost anything. Well, let's analyze this a little bit more closely, and that's how we'll end here. When this rod is rolling to the right, I have a current up, a magnetic field into the board, so I actually have a magnetic force on the wire backwards. So I'm going to draw this. There's actually a magnetic force backwards here, and let me, okay, magnetic force backwards. So that wire actually, this rod actually slows down and stops moving very quickly. So let's say it initially had some kinetic energy. That kinetic energy would be converted into electric energy to drive the current, which would then be dissipated as thermal energy in the resistor. If you want to keep it moving, you need to pull it along. F pull with the same force that's pulling it back. In that case, whatever energy you're inputting into the circuit is also going to be output at the same rate. Very final point on this one is, how does this connect to Faraday's law? Well, what happens as the rod moves to the right? There's more and more magnetic field lines poking through the loop in this direction. So the magnetic flux through the loop in this direction is increasing. Faraday's law says it doesn't like that, so a field is induced to oppose that increasing field. So the only way to oppose it is to have a counterclockwise current, which creates a field out of the board to cancel the field, to cancel the flux that's growing into the board. Now notice, this is in a sense not new physics, because it's just depending on motion. Faraday made the connection to say you get the same result if you just change the field strength and keep the geometry the same. That's the new insight, really the new insight when it comes to Faraday's